This week we are focusing on a new number or a new concept, and this is called the mole. And the mole is something that's very, very important to chemists. It's the way that chemists count atoms. So if I told you to go to a balance and weigh a single carbon atom, you couldn't do that because a single carbon atom is too small. You wouldn't even be able to see it. So when chemists are working with something that is so small, you need a pretty big number to be able to talk about them in a way that makes them make sense, and that pretty big number is the mole. So a mole is like other words that we have in the English language that describe numbers. So for example, you probably know what a decade is. You've probably heard of a decade before. And a decade, like a mole, is a word that's a stand-in for a number. So a decade is 10 years. Okay, so when you talk about a decade, you're talking about 10 years, but when we say the word decade, it conveys a number, and the mole is the same way. It is a word that conveys a number. So pi is something that gets used in math, and pi is a word that conveys a number, an infinitely long number, but it is still a number. So, you 3.1415, whatever, that is pi. And so pi is a number, but it's actually a word. And so the mole is the same way. So when you think about mole, you should actually think about the number that it actually represents. So a mole is an animal as well. You may have heard of a mole animal. Here you have a star-nosed mole, these blind animals that live underground. Or you may have heard of a mole being a growth on your face, but for chemists, a mole is a number. Okay, so chemists do it with moles. This is how chemists calculate things. They use moles. So a mole is a number. It is a big number, 6.02 times 10 to the 23rd. And so this is a 602 followed by 21 zeros here. It was discovered by this guy, so handsome. His name is Amedeo Avogadro, in the late 1700s, early 1800s, when chemistry was kind of starting to take off, and so this number is named after him, sometimes referred to as the Avogadro's number, which is why Trader Joe's used to carry guacamole, which was called Avocado's number, because it's like Avogadro. That's a funny little pun there, only people who know something about chemistry would get. So this is Avogadro's number, 6.02 times 10 to the 23rd. You're going to hear it a lot over the next few weeks, and you're going to do a lot of math with it. So the mole is defined as the number of atoms in 12 grams of carbon. This is just the base idea of it, but any number of atoms in their molar mass. So carbon's molar mass is 12. And so if you had 12 grams of carbon, you have its molar mass of carbon off the periodic table, and that is then going to contain 6.02 times 10 to the 23rd atoms of carbon. But you can do this for any element on the periodic table. That mass number on the periodic table is telling you how much 6.02 times 10 to the 23rd of that atom weighs. So hydrogen's atomic mass off the periodic table is 1.01, and so 1.01 grams of hydrogen atoms would contain exactly 6.02 times 10 to the 23rd grams of hydrogen atoms. So the atomic masses on the periodic table show you how much 1 mole of that element weighs. Not all atoms are the same size, but the mole is always the same. So 6.02 times 10 to the 23rd atoms of hydrogen would take up a lot less space than 6.02 times 10 to the 23rd atoms of gold. So their masses are going to be different, even though the quantity of atoms is always the same in a mole. Here is fluorine's box off the periodic table. This 9 refers to its number of protons, F is its symbol, 19.00 refers to its mass, and this is 19 grams to get to 6.02 times 10 to the 23rd atoms of fluorine. So if I had 19 grams of fluorine, I would have 6.02 times 10 to the 23rd atoms of fluorine, or 1 mole of fluorine. So 19 grams is 1 mole of fluorine. Here is boron. Boron has 5 protons. Its atomic mass is 10.81. So if you massed out 10.81 grams of boron, you would have exactly 1 mole of boron, or 6.02 times 10 to the 23rd atoms of boron. So let's visualize something else. This is salt. You've seen salt before. You're familiar with it. So let's say you started counting salt, and you were going to count to 6.02 times 10 to the 23rd. So those little tiny pieces of salt, which are called grains of salt, those little tiny crystals, if you spilled some of that out on your desk and you started counting, I want you to imagine how big the pile of salt would be if you got to 6.02 times 10 to the 23rd of these little pieces of salt, little tiny grains of salt. Because remember, atoms, the 6.02 times 10 to the 23rd is an enormously huge number. It's hard to even fathom how enormously huge it is, but this exercise will help you get there. So, are you picturing a pile of salt that can fit in your hands? Are you picturing, if I counted to 6.02 times 10 to the 23rd atoms of salt, would it, or so grains of salt, because they're not atoms, it's a molecule, but would it fit in your hands? Okay. Are you imagining something that would fit in a very large bowl? Are you imagining something that would fit, on the size of a desk? You could at least pile it up on a desk, or maybe on a 10-foot long table. How big is your pile of salt in your imagination that holds 6.02 times 10 to the 23rd crystals of salt? Well, the answer will surprise you. It's this big. So a mole of salt crystals, count out those little tiny salt crystals, would be as large as Miami, Florida, and would be 27 miles tall. This is what it would look like. If you could count out little grains of salt and get to 6.02 times 10 to the 23rd of them, it would be this big. And that's really hard to fathom. Like, how could it be that big? But remember, moles are never used to count something that you can see. We're using them to count things that are microscopically invisible, so very, very tiny. Whereas grains of salt, even though they're really small, you can see them. But in each individual grain of salt, you could have millions of atoms in those individual crystals. So atoms are very, very, very tiny. And so we wouldn't use moles to count anything that's visible, because that would make for a very, very large object. But moles make sense when you're trying to count things that are invisible, because they are so microscopic. So that brings us to another way of calculating moles, and that has to do with the molar mass. So this is a handy way of figuring out what 1 mole of a compound weighs. So if I have 1 mole of salt, how much would that weigh? If I have 1 mole of sugar, how much would that weigh? So here we're calculating compounds. We're not calculating individual atoms, because individual elements, their mass is just listed on the periodic table. You don't have to do any calculation for that. But elements don't just hang out by themselves, they form compounds, and so those compounds have masses, and that's their molar mass. So to calculate the molar mass, you're going to add up the total mass of each element from the periodic table, and then there are these things called subscripts. So subscripts are like H2O. When you talk about water, you talk about H2O, and that 2 is a subscript. It is telling you that there are 2 hydrogens in that water molecule and not just 1. And so if there are subscripts, you multiply the mass by that number. And here is an example. And you're going to write this down in the bottom of your Cami doc, and you can freehand tool this. So just grab the drawing tool and draw H2O is probably an easier way of doing this instead of typing it, because there's going to be some arrows here in a second. So H2O, okay, H is hydrogen, and if I go to the periodic table, I'll see that it weighs 1.01. And then there's a 2 though, so I have to multiply this 1.01 times 2, and that gives me 2.02. So the total amount of hydrogen in this compound is 2.02. And then oxygen weighs 16.00 off the periodic table, and there's only one oxygen. There's no subscript here, so I don't have to multiply that by anything. And so I'm going to take my 16 for oxygen and add my 2.02 for hydrogen, and that tells me that 1 mole of water will weigh 18 grams. It's 18 and not 18.02 because there's this thing called sig figs that I'm still trying to decide if I want to teach you or not, because they're somewhat complicated and the virtual teaching environment doesn't really lend to teaching complicated math, so I haven't decided yet. But anyway, molar mass is here, so 18 grams. If I had 18 grams of water, then I would have exactly 6.02 times 10 to the 23rd molecules of water, not atoms of water, because water's not an atom. Water is a molecule. And that's how you find molar mass, and you're going to have a couple assignments this week where you practice that.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.